Let's go ahead and continue example 11.8. So we found our omega prime to be 4 radians per second. Okay. Now, or I'm sorry, revolutions. This should be revolutions. Now we want to find the number of revolutions, right? That is the whole question. How many revolutions can he execute? So we need to find a way to calculate the time, and then therefore we can calculate the number of revolutions. So remember that from kinematic equations, that we have some y is equal to y naught plus v naught t minus 1/2 gt squared. Okay. Now we don't have any linear velocity to start with. Okay. So let's go ahead and solve for t from this. So we've got t squared is equal to y naught minus y. Okay, and then multiply the 2, divide by g, and so then our t is going to be square root of 2 times our height difference, so that's going to be 3.0 minus 1.8. So 3 minus 1.8, and then divide that by 9.8 meters per second squared, and this is in meters up here. Okay. So then we should get 0.5 seconds. Okay. Now from that we can use our angular velocity here, which is equal to 4 revolutions per second, and then multiply it by our 0.5 seconds, and we get 2 revolutions. So this gymnast can do 2 revolutions in that amount of time, from his extension to the tucking to landing. Okay? Alright, so we're going to look at our last example here, 11.9. It states a bullet of mass 2 grams is moving horizontally with a speed of 500 meters per second. The bullet strikes and becomes embedded in the edge of a solid disc of mass m is equal to 3.2 kilograms, and radius r is equal to 0.5 meters. The cylinder is free to rotate around its axis and is initially at rest. What is the angular velocity of the disk immediately after the bullet is embedded? Okay. So we are looking for some omega prime here. Okay, so what we'll do is we'll have some sort of angular momentum before and after the collision, and again it's conserved. Okay, so we want to find this angular velocity after the collision. Okay, so in this first case we will have a L1, I'll say, or L sub b from the bullet, and this will be mv times r, okay, since it is going to be our momentum times the radius. Okay, and since the cylinder is initially at rest, we don't have any initial velocity, so there is no momentum for that first, or for that cylinder at first. Okay, and then after, we will need to calculate some I for some I prime, omega prime. So our I prime is going to be m r squared for the bullet, so it acts as a point, plus 1/2 big M r squared, or we can say m plus capital M over 2 times r squared. Okay, so now we can plug this in. So we have mvr is equal to m plus capital M over 2 r squared times omega prime. So one of these cancels, so we should get omega prime is equal to mv over m plus capital M over 2. And so you can plug everything in. Oh, whoops. And I'm missing an R. Should be an R down here as well. Okay, and then once you plug everything in, we can get down here to this answer here, 1.2 radians per second. Okay, so 1.2 radians per second. Okay, so that is the last example. You may notice that there is one more section in the textbook. Okay, but I'm not going to go over that. If you're interested, please feel free to read through it. But I'm just covering sections 1 through 3 this time. Okay, so if you have any questions about anything and about homework, let me know and I will try my best to help you out. Have a good weekend.